gentlemen, and yeah, today I will talk about the cyclic material behavior of additively manufactured Incone 718 after different heat treatments. So let's start with some motivation. Why Incone? Incone is a high-string thermal resistant nickel-based alloy and is widely used in the aircraft industry. The problem with this material is its reduced and therefore very expensive machinability. Therefore, this makes him an optimal candidate for additive manufacturing applications, so that we can produce net-shaped parts. So we used this technology called laser powder bed fusion, but also previously called the selective laser melting, direct metal laser sintering. There was a little bit of confusion about the nomenclature, but now seems to be defined, laser powder bed fusion. And so mainly there is a laser which is scanning a bed of powder, and the material is growing in the direction of the laser until the net shape. The aim of this work is the derivation of the cyclic stress-strain behavior of the material when post-treatment heat treatments are applied and based on different build directions to be used, for example, for simulations. So the factors which affect the cyclic material behavior are several in additive manufacturing, and some of them we can somehow act on them. Some others are out of our control. There is the huge problem of the coupling. So let's say our first idea is that we would like to not use a global approach. So it might be really complicated by the experimental point of view to perform so many tests to have a really robust global approach which describes these materials. So what we decided to apply is the so-called material-based fatigue approach. So starting from the characterization of the material in the local system, so local approach strain-based, then going to a global one. This type of approach is described in this paper by my colleague Matthias Hell, and was also shown on Tuesday during his presentation, so I will not go on this. What we will do today here is to characterize the material, so just focusing on the first part of this diagram, so the cyclic material behavior. For doing so, we use the incremental step test, which is a variable amplitude strain control type of testing, and the specimen is subjected to this strain field, let's say. So starting with the maximum elongation, and then decreasing, oscillating around the mean value in the shape of blocks, so until the fracture occurs. And how we define that the fracture occurs? We define the last block as a decreasing of the 10% of the half of the number of blocks in terms of stress. So when we have a decreasing of the 10% respect to the half of the life, we consider the specimen broken. And this goes on until the machine stops. So what we do then with every one of these blocks, we analyze them. And for example, what we have for the first block, so here we have the shape is triangular in the field of strain, but what we have actually the stress is something that is not linear, when, for example, we have plasticity. And what we obtain is this cyclic stress-strain curve represented by the reversal points of every hysteresis. So these are the results, just as an example for some aluminum alloys. And this is what we had, for example, at the first block, and this is what then we have at the stabilized block. So for example, here we are facing a hardening phenomenon. We did the same for our material. And we performed the test on the E-cylinder, which is a test rig developed at the Fraunhofer LBF in Darmstadt. And the specimen is clamped between the clamping systems and then subjected to strain, to the strain field previously described. And the local strain is measured by means of an extensometer. The specimen is then closed inside an anti-buckling system, since a fully reversible cyclic loading is applied in our case. So R epsilon minus 1. And we performed 3 tests for each configuration with 3 different maximum strain amplitude, just to compare what happens when we increase the strain field. And what we obtain at the end is the stabilized cyclic stress strain curve. So represented by the reversal points of every hysteresis and derived by Ramberg-Osgood with the quick regression. So not so complicated. So let's start with the results. Let's describe the experimental campaign. So we produced the small-scale flat specimens. We tested the as-built states, so as well as the previous presentation, we didn't polish them because we think that is not representative of the real application. And we produced them using two different build orientations, so 45 degrees XZ and Z, and we applied superstructures for printing the specimens in the XZ directions. So we have the layers, which are oriented by 90 and 45 degrees respect to the loading direction. We applied then three different heat treatments, post-heat treatments, one up to 650 Celsius degrees, one at 760, and one at 965. And at the end we did sandblasting just to clean the specimens. So another thing that has to be taken into consideration and is usually not considered at all is the presence of these superstructures. If you want to produce structure which has let's say an orientation that is less than 45 degrees, 50 degrees compared to the powder bed, is somehow as a suggestion to use the superstructures. And how the material will look like after the removal is, for example, here represented. So here, for example, we have the superstructures with high porosity because they are produced with parameters just to improve the speed. And then we have the core material, which is the material we will test. But after the removal, there will be an area here of contact with a high roughness, which in our case reached 120 micrometer, and some pores also in the interface. And the layers will not be that regular. So let's see what we had as the first results. Just testing at 0.4%, we have macroscopically linear elastic behavior. These are the reversal point of every hysteresis for the stabilized block. And we have an increasing of the number of cycles to failure with the increasing of the temperature of the heat treatment. These for the specimens built in the Z direction. For the specimens built in the XZ direction, which means 45 degrees, we still have a macroscopically linear elastic behavior. We have also an increasing of the number of cycles to crack initiation with the increasing of the temperature, but we have a higher value of the Young's modulus. So we are facing an anisotropy inside of the material, which also has to be taken into account if we want to do simulations, for example. So what we do to the solver, to it, is this Young modulus and this Young modulus, depending on the orientation. Going on at 0.6% of the maximum strain amplitude, we see some plasticity which occur, and the hysteresis starts to be visible. And unfortunately here we have no data for the heat treatment A, but we can see, for example, what happens in the XZ direction. So we have definitely an enlarging of the hysteresis at the same maximum strain amplitude with two different build orientation. These can be done both to the fact that we are building at 45 degrees respect to the bed of powder, and both the case that we removed superstructures, so we will have local plasticity here, for example. But going on to 0.8%, the difference between the hysteresis, especially in the tension direction, completely disappear, depending on the different heat treatments. So we have that the hysteresis are overlapped in the case of the Z specimens. But this is not true in the case of the XZ, where we still can see some differences. And what we can also see from this diagram here is how the number of cycles to crack initiations is dependent on the shape of the hysteresis. So for higher level of the maximum tensile stress, we have a lower number of cycles to crack initiation, and when the maximum stress is the same, we have a lower value of the number of cycles to crack initiation for the larger hysteresis. So this is an energetic consideration maybe. Also, what we see is that if we consider the heat treatment B, for example, we have some kind of anisotropy. So if we want to consider these behavior, cyclic behavior, in case of simulations, we will have to take into account the different build orientation. This is mainly due to the microstructure of the material, which can be seen, for example, here in the orthogonal and parallel direction to the build direction, present equiaxial dendrites elongated in the build direction. Here also the green boundaries can be seen, the met pools. So here it's quite clear still the microstructure of the material. What is completely different is when we go up with the temperature of the heat treatment. In this case, here the structure is not visible anymore. So we don't see the laser paths, we see just barely the met pools, and if we go even closer, we see that some segregations are starting to form at 965 degrees. And the met pools are, as said, barely visible, and therefore we have the tendency to have an homogeneous behavior, so not isotropic behavior. But let's go to the strain life curves. I just want to point out that this is a variable amplitude loading testing, so it's not constant, this is not Euler. And what we can see anyway is that with the decreasing of the locus of the strain amplitude of the test, we have of course an increasing of the number of cycles to reconciliation, and also we have an increasing of the scatter band as we go to lower values of the strain amplitude. This is also as expected, let's say. Then we have that for the specimens built up in the z directions, we have a higher values of the number of cycles to reconciliation, more or less. This is a bit confused here for very high levels of the strain amplitude. And at the end we have that as we move to lower values of the strain amplitude, the number of cycles to crack initiation for the heat treatment C with higher temperature leads to a longer fatigue life for the specimens. So just concluding, the material Incone 718 produced by additive manufacturing presents an anisotropic behavior for cyclic deformation linear to the linear elastic field. And in particular present a higher Young modulus for the specimens built in the XZ direction. This we also found for other materials. So this we have reasons to think that is due to the chronological process and not to the material. The cyclic behavior is independent to the heat treatment along the build direction Z, while along XZ it varies significantly. The shape of the hysteresis affects the fatigue life, so we have that for a higher maximum stress loads, leads to a lower number of cycles to crack initiation, and wider hysteresis also lead to a shorter number of cycles to crack initiation. And then we have that the Z direction as well as the heat treatment C results in a higher fatigue strength. And finally that the heat treatment C cause a modification and redistribution of the microstructure inside of the material, which lead to an anisotropic behavior, especially for high values of the strain amplitude. And that's it. Thank you. Question.